Hello, Earthlings. Professor Sargent here with you again. Before I get back to my series on conjectures and exploring an open-ended problem and then proving a result, I wanted to revisit a response that I made to Cybermath, another creator. He was looking at 33 to the fifth power compared to 63 to the fourth power and asking which one was larger, and also asking people that were viewing and responding to him if they could come up with other methods. He showed two methods. I posted a video not too long ago that showed another two methods, and I've come up with two more since then. I'm going to show one of them in this video, and shortly I will also record and upload the second additional method I found. So there will be a total of 6 methods. There's nothing particularly slick about this method. It's a lot of direct computation, but it is accessible. What I will be doing with looking at comparing 33 to the fifth power versus 63 to the fourth power is dividing the first 33 to the fifth power by 63 to the fourth power. If it turned out that those were equal, then 1 divided by the other would give us 1, because obviously neither one of these are 0, so we don't have to worry about 0 divided by 0. If, however, the 33 to the fifth is larger, then dividing a larger number by a smaller number will give us something greater than 1. And if 33 to the fifth is less than 63 to the fourth, then we will get something that is smaller than 1, but it's going to have to be greater than 0 because we're dividing a positive by a positive. So here we go. First of all, the prime factorization. First of all, 33 is 3 times 11, and that's all being raised to the fifth power. And 63 is 9 times 7. That's all being raised to the fourth power. I'm going to rewrite 9 as 3 squared while keeping the numerator the same. For lack of a better word, distributing that exponent across the multiplication. So that in the numerator, we've got 3 to the fifth times 11 to the fifth. Whereas in the denominator, we've got 3 squared to the fourth times 7 to the fourth. Not doing anything with the numerator at the moment. With those two exponents right next to each other, we can multiply the exponents of 2 and 4 down there in the denominator. Then I'm going to reduce. 3 to the fifth over 3 to the eighth is 3 to the negative 3, but I can put that in the denominator as 3 to the third power. So I'm left with 11 to the fifth in the numerator, and in the denominator, 3 cubed times 7 to the fourth. Again, there's nothing particularly slick about this approach, but I am going to use the binomial theorem to compute 11 to the fifth. So let me scroll down a little bit here. 11 to the fifth power. (11) is 10 plus 1. And I've got all that raised to the fifth power. By the binomial theorem, I would have 10 to the fifth plus 5 choose 1 times 10 to the fourth times 1 to the 1 plus 5 choose 2 times 10 cubed times 1 squared plus 5 choose 3 times 10 squared times 1 cubed. Plus 5 choose 4 times 10 to the first power times 1 to the fourth. And finally, now I could have said back here with the 10 to the fifth that was 5 choose 0, but that's just 1. And also multiply that by 10 to the fifth times 1 to the 0. But 1 to the 0 is 1. So on this last term, I have 5 choose 5 times 10 to the 0 times 1 to the fifth. But 5 choose 5 is 1. 10 to the 0 power is 1. And we would have 1 to the fifth power. Now, all those cases where we have 1 to a power, that's still going to be 1. And multiplying by 1 won't change anything. So 10 to the fifth, I have 100,000. 5 choose 1 is 5. We have then 5 times 10,000. That came from the 10 to the fourth. But also 10 times 10 cubed here is 10 to the fourth. So 10 to the fourth is 10,000. We've got this 5 times 10,000. Plus another 10,000. 10 times 10 squared is 10 cubed, which is 1,000. 5 times 10 is 50. And also adding 1. Combining these like terms, that's going to be 6 times 10,000. So in the end, we have 100,000 plus 60,000 plus 1,000 plus 50 plus 1 for a grand total in the numerator of 161,051. Again, that was that 11 to the 5th equals 161,051. Now we're going to work out what 3 cubed times 7 to the 4th is. All right, so to figure out what 3 cubed times 7 to the 4th is, what I've done is rewrite 7 to the 4th as 7 cubed times 7. And I'll use the same property of exponents that I first applied, but in the reverse direction. So that would be the same as 21 cubed times 7. And again, I'm going to work out what 21 cubed is by the binomial theorem. Rewriting 21 as 20 plus 1. All of that to the 3rd power. So we would have 3 choose 0, which is just 1, times 20 cubed, times 1 to the 0, which isn't going to change that. Then plus 3 choose 1, which is 3, times 20 squared, times 1 to the 1st power, plus 3 choose 2, which is also 3, times 20 to the 1st power, times 1 squared, and then 3 choose 3, which is 1, times 20 to the 0, times 1 cubed. Since 2 cubed is 8, and we have 1 extra 0 there, 20 cubed is 8,000. Since 2 squared is 4, and we have that 1 extra 0, then that's going to be 3 times 400 for that second term. Just multiplying by the 1 won't change anything. Similarly, multiplying by 1 squared, that's still 1. 20 to the 1st is still 20. So 3 times 20. 20 to the 0 is 1. 1 cubed is 1. Multiplying those together, we just have 1. So 8,000 plus 1,200 plus 60 plus 1 is going to give us 9,261. That's just the 21 cubed part. I still have to multiply that by 7. I'm not doing anything fancy for this one. 1 times 7 is 7. 6 times 7 is 42. So I write down the 2 and carry the 4. 2 times 7 is 14. Carry the 4, 18. I've got 1 to carry. 9 times 7 is 63. Carrying that 1, 64,827. So our denominator, 64,827. Because the numerator is greater than the denominator, and they're both positive, then this fraction, or the result of this division, would be greater than 1. Therefore, 161,051, that is greater than 64,827. And if we were to multiply top and bottom by the 3 to the 5th power that we had reduced by here, since that's positive, that will keep that going in the same direction. So we would have 33 to the 5th equaling 3 to the 5th times 161,051 greater than 3 to the 5th times 64,827, which was equal to 63 to the 4th power. So our conclusion is that 33 to the 5th power is greater than 63 to the 4th power. That's the same conclusion that Cybermath drew in his original video with the 2 different methods he had shown. And when I posted my response with 2 other methods, that was the same result. Again, I haven't done anything very slick there, just that in terms of dealing with the multiplication or those exponents with large numbers, applying the binomial theorem so that I wouldn't have to use a calculator. Other than that, things were pretty direct, but again, hopefully quite accessible. And I will film the other one shortly and upload that shortly.